All right, welcome back. So what I want to do now is really quickly take the three algorithms that we've learned so far, the three sorts, and compare them. So it will be a quick wrap up, but basically we've been working on each algorithm individually. We've been talking about the pros and cons, but we haven't really seen how they all compare. And you can see that they're grouped together in this section. I called them elementary sorting algorithms. They're often called quadratic sorting algorithms because their big O, their time complexity of all of them is O of n squared. Remember, we care about worst case. That's the point of big O. But we also broke it down into average, so you can see O of n squared for all of them. But then if we look at time complexity, there's a bit where they differ. So here's bubble sort, and this is with almost sorted data. So that's the best case. If our data is totally sorted, bubble sort works really well because it goes through and it has to do very few swaps. We iterate over and we do one more check and it's all sorted and we're done. And that's it. So bubble sort performs very well in that situation. Same thing with insertion sort. If we work with nearly sorted data, we place things in the correct spot, but then you look as we go, we don't really have to do anything. We're just checking each item to the one before it, and we don't have to do any swaps. So we basically iterate through the loop once, doing one comparison for each item. If the data is totally sorted, that is. In this case, it was almost sorted. So insertion sort works well in that situation. Selection sort, however, doesn't fare so well. If you look what happens, here's nearly sorted data. We're still going to go through each time to find the lowest item. So we iterate all the way through, and it happens to be the first item. Then we do it again, and we look for the smallest, the minimum item. It doesn't matter that it's already almost sorted. So selection sort does not perform well in this situation. But selection sort is very simple to understand, which is pretty much its only positive. So returning back to this sorting algorithms animations website, if we look at nearly sorted, so there are a bunch of algorithms we haven't talked about, but we'll learn about some of these like merge sort coming up. But if we click nearly sorted, focus on how insertion, selection, and bubble perform. You'll see insertion and bubble finish very quickly. Selection takes forever. But still, insertion and bubble, which are generally slower than these algorithms, the more advanced ones, they still perform better on nearly sorted data. Okay, so that's the time complexities. Basically, they're all O of n squared, except with nearly sorted data, bubble and insertion perform well. Now, space complexity, they actually are all the same as well. And that's because we're not really using much space with these algorithms. Everything's happening in place. We're not actually creating new arrays. It doesn't matter how long the array is. We're not creating a variable for each element or two variables for each element or something like that. But what you'll see later on, some of the other algorithms that are faster, what they do is that they actually create a bunch of smaller arrays. For example, merge sort, which we'll learn next at the beginning of the next section, its space complexity is not O of 1. It's not constant. But for these, they're all basically the exact same. One thing about insertion sort that is special, that I mentioned already, is that it works very well if you need your data to be continuously sorted, so new elements are being added. So it's not a one-time thing where you have all the data ready. If we're using insertion sort, and I add in the number, 39, for example, insertion sort just needs to do basically a single pass to figure out where to put that. Versus if we were doing selection sort, it would resort the entire thing. It's not able to figure out exactly where it goes right away. So insertion sort works well in those situations. If you have data coming in and you need to resort things over and over and over and maintain a running sort, keep things up to date. Okay, so lastly, I just want to recap what we covered. Sorting is very important. It's a fundamental thing in programming. It's also very common in interviews. We'll talk more about what actually you need to know. If you are interviewing and you're concerned about sorting, you do not need to just sit here and memorize implementations of all of these algorithms. We'll talk more about what you do need to know. So bubble sort, selection sort, and insertion sort are all roughly equivalent in the grand scheme of things, especially when we compare them to the next batch of algorithms we're going to learn in the next section. There are some slight differences between these three, but they become insignificant when we see how much faster some of these other algorithms are. So they all have average time complexities that are quadratic. We can do better though, and that's what's coming up next. We need more complex algorithms. They are a little trickier to explain. They're less, I don't want to say less human. They're less intuitive right off the bat. So it's a little more work, But these algorithms are definitely worth knowing. And also, what we'll see in the next video or in the next section, these algorithms actually can perform better on very small data sets. So we'll see why that is. So these aren't a complete waste of time to learn. If you're worried about that and you're thinking that, oh, he's just showing the dumb ones first so we can get to the hard ones afterwards, that's only partially true, because these actually do excel when the data sets are small. All right, so in the next section, we're going to start learning about some of these scarier algorithms. We're going to take our time though, so hopefully it's not too bad. And we're going to start off with merge sort.